This is a lesson on impulse and angular momentum in the units of momentum and rotational dynamics. We've seen the idea of impulse before with linear momentum. After we defined what linear momentum is, we used Newton's second law in order to motivate the relationship between a force applied for a certain amount of time and the change in the linear momentum. And just like other linear quantities have been studied in rotational motion, we can see that there is an analogy between impulse for linear motion or translational motion and impulse for rotational motion. There's some sort of external force or torque on a system applied for a certain amount of time, which causes a change in the momentum, whether it be linear or angular. And so when we're looking at rotation, we can now incorporate Newton's second law into rotation, especially with collisions. And we'll see this in our next lecture on conservation of angular momentum. Torque has been defined in previous lessons, and there are multiple ways in order to calculate the magnitude and find the direction of torque. Also, angular momentum has been defined in previous lessons, and we can use these definitions and these equations in order to solve problems. I've picked out one problem for us to work through in order to exemplify Newton's second law with impulse and angular momentum. Bicycle brakes. The coefficient of kinetic friction between bicycle brakes and the rim of a bicycle wheel is 0.64. So we have the coefficient of kinetic friction. That's not the force, but that's the coefficient. The brake is applied so that both brake pads press against the rim at 40 newtons. The wheel can be assumed to be a hoop with a diameter of 66 centimeters and mass of 2.5 kilograms concentrated at the rim. So I've drawn a hoop down here for us so this can model our wheel. And they're telling us that there is a radius for this hoop. 33 centimeters is going to be the radius if the diameter is 66. They tell us the mass is 2.5 kilograms, and they tell us there's a hoop, and so the moment of inertia of a hoop is mr squared. So we have some inertial quantities going on, which we will need for Newton's second law. We also see some information about a force. Some sort of kinetic frictional force is going to be used on the bicycle wheel. It asks how long must the brakes be applied to bring the bicycle wheel to a full stop. Okay, full stop. So there's a V final is 0. If a point on the outside of the wheel is moving at 15 miles per hour. So I'm thinking about these forces being applied to the wheel, causing the wheel to slow down and stop. There's some sort of initial speed, and I'm going to make note that it's rotating maybe in this direction to begin with. And so some point on the side of the wheel will have a tangential velocity, which they tell us is 15 miles per hour. Through the relationship between the linear quantity and the angular quantity, I can write down V equals omega r. Well, the two forces are being applied to the wheel, and I can draw a quick sketch here so you can get an idea of what's going on. So there's maybe the tube of the tire, and there's some sort of rim here. And they're saying that the brakes apply forces from both sides. That's how a bicycle wheel works, is the brakes are applied from both sides. And they're telling us that those applied forces are 40 newtons, the applied forces, and there's two of them, one on each side of the wheel. So when I think about this wheel turning in the counterclockwise fashion here, there's going to be two forces causing some torque on the outside. And I'm going to put 2 times the force of friction here, right? We have a kinetic friction force. And it seems like these forces that are being applied by the brakes are what we can call the normal force for a friction. So when I look at the friction force, it'll be the coefficient of kinetic friction times this applied force is the normal force, and there's two of those, such that there's some sort of angular acceleration in the clockwise direction. There's some slowing down. So when they ask how long must the brakes be applied, I think of time, and I see up here that torque applied for a certain amount of time causes a change in angular momentum. So if I want to solve for time, I'll take the change in the angular momentum and divide by the torque. And I'm going to leave these as magnitudes. This will just be the magnitude of this and the magnitude of that. So even if they're in positive or negative direction, we can still find a time. And when I think about this in a little bit more detail, I know that delta L is a L final minus L initial, and we'll remember to take the positive value of that. On the bottom, we have some torque caused by these two forces, the two friction forces, and I'm going to note that they're being applied a distance r away from the pivot point at an angle of 90 degrees. So I'm going to have the torque of these friction forces. Let's look a little bit more detail in the angular momentum. L initial depends on I omega initial. This is a rotating object. It's an extended body. I cannot use the equation for a point mass for angular momentum. I have to use the equation containing the moment of inertia. L final is 0 because velocity final is 0. And I'm going to make note over here initial velocity and omega initial over here, so I can write this equation actually as V initial over R. So I'm getting some pieces together. I have L final and L initial in terms of values I was given in the problem to begin with. The other term I need to think about here is the torque by the friction force. Torque, I have the equation up here, RF sine theta. We decided this is the R of the wheel. The force being applied is 2 of the friction forces, and they're being applied at 90 degrees. Sine 90 is 1, so I'm going to keep writing out here. We have R times 2 friction forces, which is 2 times mu times those applied forces from the brakes on the side. And that's saying that the friction force has to equal mu times the normal force. And the normal force here in this situation is those 2 applied forces. Okay. So we have an equation for the torque. I'm going to bring all these together and plug them into my equation. I'm going to have the absolute value of 0 minus I. Well, I know what I is, mr squared. R squared times V initial over R, and that's an absolute value, divided by, I took the 2 forces of friction into account twice, so let me make sure that's accurate. I only need one factor of 2 in the denominator here, and then I'll end up with R mu times the force applied. Okay. So I have an equation together, and really all I need to do is some algebra and simplification here. I'm going to notice that there's an R here and an R here, and that cancels. And then I'm also going to notice there's an R in the denominator and an R in the numerator, and that cancels. And when I simplify, I'm going to remove the negative. I don't care about negative. It's a time. I don't want to deal with negative time. So I get mass times that initial velocity divided by 2 mu times the applied force. And when I plug numbers in there, that will give me the time. The mass, they give me 2.5. The initial velocity is 15 miles per hour. Well, I did some calculations before I started this lesson. 15 miles per hour is actually 6.7056 meters per second, so I can plug that value in here, 6.7056. I'm going to divide by 2 times the coefficient of friction, 0.64. And the last term I need in here is the applied force, 40 newtons. So there's 2 friction forces, and there's some sort of initial angular momentum. When you run this through your calculator, you get the time is 0.3274 seconds. So about a third of a second it takes to come to a complete stop when someone squeezes the brakes and applies this much force to the